Imagine this, you're designing a product ad. You have a high-resolution image of a luxury watch, its intricate engraving, the subtle texture of the leather strap, the tiny logo on the dial. You want to place it in a dynamic urban scene, with sunlight glinting off its surface. You use a state-of-the-art subject-driven generation model. The result? The composition looks perfect. The lighting is realistic. But the watch, it's blurred. The engraving is gone. The logo is distorted. The identity is lost. This isn't a flaw in the model's imagination. It's a fundamental limitation in how current AI systems handle fine-grained visual fidelity. They prioritize global realism and semantic coherence, what looks plausible, over the precise replication of small details. And in commercial applications, that's catastrophic. A misrendered logo breaks brand trust. A distorted product texture undermines credibility. A single missing letter in a tagline makes the entire image unusable. This is the core challenge behind subject-driven generation, the ability to take a reference image of a subject and seamlessly embed it into a new scene while preserving its identity. Despite impressive progress in models like Flux, One Context, Qwen-Image-Edit, and Nano-Banana-Edit, fine details still vanish under the weight of perspective, scale, and the ambiguity of language-based conditioning. Today, we introduce FlowFixer, a new refinement framework that doesn't just improve subject fidelity, it redefines what's possible in high-fidelity, detail-preserving subject-driven generation. Let's break down why this matters. Most subject-driven models rely on text prompts to guide the generation. A red sports car on a mountain road, but what does red mean? What's the exact shade? What about the logo on the hood? The texture of the tires? The reflection in the windshield? Language is inherently ambiguous. It captures broad semantics, not precise visual structure. Even when models use image-based conditioning, like depth maps or edge cues, they often prioritize global scene coherence over local detail. The result? High-frequency information, fine textures, logos, tiny patterns, gets smoothed out, blurred, or lost entirely during diffusion. And here's the catch. Collecting real, high-quality paired data, where you have a clean subject image, a generated image, and a ground truth output with perfect alignment, is nearly impossible at scale. Real-world SDG applications rarely come with such annotations. So how do we train a model to restore what's missing, without needing labeled data? Enter FlowFixer. At its core, FlowFixer is a model-agnostic, prompt-free, image-to-image refinement framework. It takes two inputs, the generated image from any SDG model and the original subject reference image. Then it learns to correct the generated image, not by reimagining it, but by reconstructing the missing details from the reference. No text, no masks, no manual intervention. Just a direct visual translation from what's broken to what's right. But how do you train such a model without ground truth labels? Here's the clever part, self-supervised pseudo-paired data. We start with a clean, real-world image, say, a photograph of a coffee mug with a complex logo. Then we simulate the kind of degradation that happens in real SDG. We add noise to the image, then apply a single-step denoising using an off-the-shelf diffusion model, like SDXL. This process mimics the exact kind of high-frequency detail loss seen in real subject-driven generation. Small textures vanish, fine lines blur, logos warp. But crucially, the global structure remains intact. The mug is still the mug. The scene composition is preserved. We call this one step, denoising a degradation simulation. And we repeat it across 3 levels of severity, 1, 0 times 0, 5 times and 0, 25 times the original resolution, each simulating different degrees of scale and perspective change. Now we have a pseudo-paired dataset. Each degraded image acts as the generated input, and the original clean image is the reference. The model learns to go from the degraded version back to the original, restoring what was lost, without ever seeing the true ground truth. To train the model, we use a simple but effective mean-squared error, MSE, loss between the refined output and the clean target. But we don't just rely on pixel-level metrics. We use a more intelligent approach, keypoint matching. Because the real goal isn't just to make the image look similar, it's to make it structurally consistent. A watch with the wrong number of dots on its face. That's not fidelity. A mug with a logo in the wrong orientation. That's not identity. So we use a pre-trained keypoint matching network, OmniGlue, to find dense correspondences between the reference and the generated image. We measure 2 metrics. Absolute keypoint increase, AKI, how many more keypoints are matched after refinement. Keypoint matching gain, K Gain, the percentage of cases where the match improves. These metrics are ground truth-free, reproducible, and highly sensitive to fine-grained structural changes, something CLIP or DINOV2 simply cannot capture. They're designed to detect when a model restores actual detail, not just fake realism. And the results? They're striking. On our new benchmark, Fidelity Bench 258K, a large-scale, diverse dataset of 258,000 subject, prompt pairs, we tested FlowFixer against 3 leading SDG baselines, Flux, One Context Pro, Qwen-Image-Edit, and Nano-Banana-Edit. The numbers tell the story. FlowFixer achieves an AKI of 66.5 on Flux, One Context Pro, more than 10 times the baseline. It improves K Gain to 77.9%, meaning in nearly 8 out of 10 cases, the model consistently restores structural alignment. And crucially, this improvement isn't reflected in clip or dyno scores, because those metrics don't care about fine details. They care about semantics. But FlowFixer does care. And it wins. Qualitatively, the difference is even more dramatic. Look at the zoomed-in regions. The complex architecture of a building facade. Restored. Small text on a product label. Legible again. The subtle facial features of a person. Preserved even under rotation or viewpoint change. Color shifts. Corrected. And all without altering the global layout. No composition drift. No unnatural artifacts. This is because FlowFixer uses a dual-stream conditioning mechanism in a shared spatial space. The reference image and the generated image are encoded separately but processed together in the DI-T backbone with 3D row P, a positional encoding that maintains stream separation while enabling full cross-attention. This allows the model to learn local correspondences, to understand. This pixel in the reference maps to that pixel in the generated image and correct deviations with surgical precision. But here's a practical breakthrough: crop-based refinement. Generating a full image at high resolution is slow and memory-intensive. So instead of refining the entire image, FlowFixer first detects the subject using keypoint matching between the reference and the SDG output. It crops the subject region, refines only that part, then blends it back using Poisson image blending. The result? A massive speedup, up to 4x faster inference, while maintaining or even improving subject-level fidelity. The background stays unchanged. The layout is preserved. Only the details are fixed. And when we compare full versus crop-based refinement, the crop method wins because it focuses computational power exactly where it's needed, on the subject. But the real test? Human judgment. We ran an A/B study with Amazon Mechanical Turk, showing raters the reference image alongside two candidates, the baseline and FlowFixer. Across 300 test cases, FlowFixer was preferred in 91.2% of cases, a massive margin over alternatives. Even more telling, we used a vision language model, Claude 3.7, as an automated judge. It agreed with human evaluators, and its decisions aligned perfectly with our keypoint metrics. This cross-validation proves that AKI and K Gain aren't just numbers. They reflect real perceptual improvements. And one final insight: training with diverse degradation levels matters. We trained versions of FlowFixer with only slight noise, 1, 0 times, moderate noise, 1, 0 times 0, 5 times, and full distortion, 1, 0 times 0, 5 times 0, 25 times. The model trained on the full range consistently outperformed others, especially under large-scale distortions, proving that diverse degradation simulation is key to robust real-world performance. So what does this mean? FlowFixer isn't just a new model. It's a new paradigm. It's agnostic. It works with any SDG model, no retraining needed. It's prompt-free, no ambiguous language conditioning. It's self-supervised, no expensive paired data. It's highly efficient. Crop-based refinement enables real-time use. And it's evaluatable, with metrics that actually measure what matters: fine-grained structural fidelity. In short, FlowFixer closes the last-mile gap in subject-driven generation. It takes a model that almost gets it right and makes it perfect. And this isn't the end. Future work includes multi-reference refinement, using multiple images to guide a single generation, and interactive correction, where users can provide scribbles or sparse feedback to guide the refinement. But for now, FlowFixer sets a new benchmark, a new standard, a new level of fidelity. Because in the world of AI-generated content, it's not enough to be realistic. You have to be accurate. You have to be true to the subject. And that's exactly what FlowFixer delivers.